what we're going to start off with is just some basic pattern finding type questions. And these are not going to be, well, I guess we'll see, but usually these are neither arithmetic nor geometric. So you need to kind of think outside the box, but it's not too bad. Like, let's start with this one. It's a very weird looking sequence. We start with x plus 1 over y, so that's our first term. And our second term is 2x plus 1 over y squared. And our third term is 3x plus 1 over y4. So this is t1, this is t2, this is t3. What's going to be t4 if you follow this pattern? Look at the x's. How many x's will we have for the fourth term?
4.
4, right? And what's going to be the power of y down here? This was supposed to be a 3. So for the fourth term, what's the power? It's going to be 4 as well, right? Like that?
Mhm.
So now the question is, what's the expression for the general term? So let's say we wanted to find Tn. How many x's will we have for the nth term? There's going to be an n number of x's. So n times x. What's going to be the power of y?
N.
N. There we go. So this is your general term. So that one wasn't too bad. And this will give you anything, like T100 would be 100x plus 1 over y to the 100. So with the general term, you can find any term. All right, so here we have a fraction. So usually when you have a fraction, you want to do it individually, as in like the numerator and denominator, you want to do them individually or independently. Let's look at the numerators. 321, 147, 1029. Let's just look at the first three. What do you think is happening here? How do you get from 3 to 21?
You multiply by 7.
Yeah, that's it, right? So in the numerator, it's easy. So let's see if we can come up with a pattern for the numerator. So T1 is 3, T2 is 21, so we multiplied this by a 7. What would be Tn?
N minus 1 times 7.
Don't think that's gonna work, because if you look at T3, you're gonna end up getting just a 14 if you use this rule. Right?
Oh, yeah.
But if you just fix this, if you do that as a subscript, then I think it's gonna work. This rule. Where the next term is the previous term times a 7. Yeah?
Mm-hmm.
So that would work. This is just a linear function, I think. Let's see if we can just figure this out. So it's not a linear function because you're multiplying by a 7. This is gonna be a geometric series, right? Or a sequence, sorry, not a series. It's a geometric sequence. Our first letter is an A. So this is if you want to do it using a recursive. But I don't know if this question wants a recursive. I think they want a general rule. So let's come up with a general rule for this. So your first letter is a 3. We're multiplying by R of 7, right? That's our common ratio. So your general form is going to be A times R to the n minus 1. There we go. So in this case, it'll be Tn, the nth term will be 3 times 7 to the power of n minus 1. So that's the general rule for the numerator. Cool? I can double check this, right? Let's double check. Because for T3, we're expecting 147. So 3 times 7 squared, that's 3 times 49, and that is 147. So it checks out. So that's our rule for the numerator. Now let's come up with a rule for the denominator. What's happening here? 555 and 555. Do you see the pattern? We're adding an extra digit of 5, yeah? If you ever do computer science, you're gonna be stuck with logical arguments like this one, for which you need to find a pattern. Even though it's not a math question, at that point it becomes a math question. The pattern here is this. You multiply by 10 and you add a 5. You multiply by 10 and you add a 5, okay? So T1, so what's gonna be the general pattern then? Let's say we wanna find T4. Well, we know it's gonna be do you agree with this? Here, this one is not a geometric or an arithmetic sequence. It's because we're doing both at the same time. For it to be one or the other, like we did in the previous question, wouldn't work here. So I guess a general form for this pattern, I guess you could say like this. Tn is going to be in the numerator, you multiply that by a 7, and in the denominator, you will multiply that by a 10 and add a 5. Okay, like that. So this would be a recursive relationship. I can't really write it in this form because it's not a pure geometric or pure arithmetic sequence, but that will give you the next term. So if you have a fraction, it's probably best to split it apart into numerator and denominator. It does get very tricky very, very easily. And this one's a fairly simple pattern. What's the pattern here?
You multiply by 2 and you add 1.
Yeah, that's it, right? Easy peasy. That one's pretty simple. So here, what's the next digit? what comes after 90 is the pattern.
It's 85.
Yeah, exactly. It's 85, and then it's going to be 79 and 72. 85 minus 5 minus 6 minus 7. You agree with that?
Mm-hmm.
Not that bad. This next one is actually a very famous sequence. This one's hard, unless you see it. Once you see it, it's very, very easy. The math is very simple, but you have to be able to see it. I'll give you a hint, right? The question is, what's the next term? That's the question. And the hint is this. You need to use the previous two terms to get the next term. So far, usually we only use one previous term, but for this sequence, you need to use two of the previous terms to get the next term.
You add them.
You add them. So what's the next term?
34.
34, yeah. And the next one will be 55. The next one will be 89. Okay?
Mm-hmm.
This is called the Fibonacci sequence. This is very prevalent in nature. What about this one? The question is, what's the next digit? So here the pattern is it's an alternating pattern. So from here to here, we added a
You add
2.
2 and then you multiply by
So
2.
what's the next digit? Is it 54 or is it 104? So I guess you have two
54.
choices. So we multiplied by 2. So we
Then you add
must, so this is the next number. And the next one would be 108. And the next one would be 110, okay?
Mm-hmm.
So that's the sequence for that one. What about this one? So this one is has nothing to do with the previous term. Again, you need to realize that these are cubes. And in fact, these are alternating cubes. The signs alternate. So the next digit must be negative, right? This is 1 cubed. This is negative 2 cubed. This is 3 cubed. That's negative 4 cubed. This is 5 cubed. So the next one must be negative 6 cubed, yeah?
Mm-hmm.
The cube doesn't affect the negative sign. This will still become a negative number. The next one will be positive 7 cubed, and the next one will be negative 8 cubed. So these three would be the next three terms of this sequence. The next one's simple. It's just times 2 plus 1 for f. Not gonna bother with that. Times 2 plus 1 for this one. Pretty easy. Okay, what about this one? What's the pattern? So this one is tricky in the sense that it depends whether the previous number was odd or even, okay? So starting off with the 2, it's an even number. We multiply by 5 and we add a 1. So if you can write it like this. So our T1 is a 2, that's easy. Tn, the next term, if the previous term is even or if the previous term is odd, the rules are going to change. So if it's even, how do we get the next term? You multiply the previous term by 5, yeah?
And then add 1.
Add 1. What about if it's odd? You multiply the previous term by 5 as well, but do you add 1 or do you subtract 1?
Subtract.
Subtract, there we go. So that's the pattern for the next one. And it continues. So you can write it like this as a rule, as a recursive rule. The next term is always dependent on the previous term. And it says the next 3 terms, well, again, it's going to be this times 5 plus 1, because this is even. And the next number would be whatever that is times 5 minus 1. And the next number would be whatever that is times 5 plus 1. Okay?
Mm-hmm.
You can just use this pattern here. So you can write it as this pattern using a recursive rule. All right, let's try this one. They've given us a pattern and we need to find the 1000th term. Looks tricky. There's no way we need to list out all thousands for them. There is a shortcut. So it's going to depend whether we see it or not. So the first term is a 1, which is an odd term. So we go down here. So the next term would be 5 over 2 times the previous term, which is a 1 plus 1. So it is 5 over 2 times 2. The next term is 5. Okay?
Mm-hmm.
And now we have another odd term. We need to do the same thing again. We multiply it using the bottom rule. So T3 would be 5 over 2 times T2 plus 1. So here it'll be 5 over 2 times 5 plus 1. That's 5 over 2 times 6. So that's a 15. Again, we have an odd number, so we go down here. The next term would be 5 over 2 times 15 plus 1. That's 5 times 8. That's a 40. Now it's even. We go over here. The next term would be half that, so that's 20. The next term would be half that, that's 10. The next term would be half that, that's 5. And look at this, the pattern is going to repeat. Because we're back down to 5, and if we follow the rule, it's again going to be 15, 40, 20, 10. So this is our T1, T2, T3, T4, T5, T6. So every 6 terms, the pattern will repeat, okay?
Mm-hmm.
Or actually, this is T7, T8, T9, T10, T11, like that. And the next one would again be 5. So T12 would be 5. And then the pattern would start again. T13 is 15, 40, 15 is 20, 16 is 10, and then 17 is 5 again. So now the question is, what's the 1000th term? Let's look at it this way. So from this 5 to this 5, we had 5 terms, right?
Mm-hmm.
So every 5 terms, 1, 2, 3, 4, 5. So every 5 terms, the pattern repeats. So that means T6, if we add a multiple of 5 to this, let's say 5 times, because we need to get all the way to 1000. So 5 times 199. So this will give me my, so this is T6 plus 995. So I know at the 996th term, I'm right back up here. Sorry, right back up here. You just need to add a multiple of 5. And this total needs to be less than 1000. So that's why you can't put a 200 here, because then it would be more than 1000. You would have overshot it. You want to see the previous sequence. So we know our 996th term is a 10. That means this is 997, 998, 999, and our 1000th term is a 20. Right there. Okay?
Mm-hmm.
And that's going to be the answer to this question. So this one, again, it's difficult because it doesn't follow a singular sequence. It's a combination of both geometric as well as arithmetic. In that case, it becomes a lot more difficult. You have to really think outside the box like we did here. I'm sure there's other ways to do this. That's just one of them, where you see where the pattern ends. All right, let's try something else. Let's try this one. So we're given the first term and the second term, and we're given a pattern, a recursive pattern that uses the previous 2 terms to get the next term. And the question's asking us to generate the first 10 terms. All right, cool. This one isn't as hard. So look at this, T3, I'm gonna follow this pattern. We're given the first term and the second term. T3 would use T2 plus 2 times T1, like that. T4 would use T3, yeah?
Mm-hmm.
Plus 2 times T2. So the previous term and twice the number that was 2 terms away. So here for T3, it'll be 5 plus 2, that's going to be a 7. So 157. T4 uses T3, which is a 7, plus 2 times T2, which is a 5. So that's 7 plus 10, that's a 17. T5 would use 17 plus 2 times the term that was 2 away, so that's going to be times 7. So that's 17 plus 14, that's a 31. Yeah? T6 would use 31 plus 2 times 17. That's 31 plus 34, 565. T7 would use 65 plus 2 times 31, 65 plus 62, 127, like that. And you can keep going up until the 10th term. We don't really need the 10th term. So our general pattern is 1, 5, 7, 17, 31, 65, 127. Let's just stick with this. Part B says calculate the ratio of consecutive terms. Sorry, let's do here. 5 over 1 is a 5. So the first ratio is a 5. If you do T2 over T1. The second ratio, if you do 7 over 5, is going to be 1.4. The third ratio will be 17 over 7, which is a little bit more than 2. It's 2.43. The next ratio will be 31 over 17, which is 1.82. The next one is 65 divided by 31, 2.09. The next one is 127 divided by 65. It's 1.95. What's happening to the ratios? It's approaching a certain number. What number is it approaching? If you look at these numbers, it's approaching, it's going towards a certain number. What is that? And I think that's what it's asking us. The next one will be 2.023. The next one will be 1.99. You see the pattern? Where is it headed towards? It's headed towards a 2, yeah? So the next one is 2.0058. So the answer to part B is that the ratios are approaching 2. Cool? So if it approaches 2, is it a arithmetic sequence or is it a geometric sequence? If it approaches 2, then it'll probably be a geometric sequence. But the thing about this is that it'll never actually approach 2. It's going to get closer and closer, but it'll never actually be exactly 2. So here, let's find the pattern. And the pattern is this. Because we're approaching 2, we know we have to multiply by a 2, okay? We're going to multiply by a 2 because that's what the ratio is approaching. Try and see the pattern. What do we need to do to 1 to get a 5? We know we're multiplying by a 2. And then what do we need to do?
Add 3.
Add 3. What about 5 to 7?
Do the same.
You need to
Oh, no, no.
subtract, right? And then from here to here, you times and add. There we go. That's the pattern. Here to here, 34 minus 3. Cool? So I guess for the general term, we know T1 is a 1. And for Tn, I guess we can write it like this. So if n is odd and if n is even, N means the term number. So the term number is odd, like the first term, the third term. See if the pattern holds. It does hold. So for this, if your term number is odd, you're gonna multiply by a 2 and you're gonna add a 3. And if your term number is even, like for these guys, what do you do to get the next term?
You subtract 3.
Yeah, you add, multiply 2. And there we go. I think that's the answer to this question, okay?
Mm-hmm.
So again, tricky. That's just how these questions are. Let's start with this one. It says determine the 15th term of the sequence and explain your reasoning. Do you see it? Take a minute because it's question is what's the next term, I guess. If you see it, you see it. Any ideas? It's definitely tricky. I'll give you a hint. And this is again, so we've already done this pattern, but to find the next term, you need to use the 2 previous terms. Tn is dependent on Tn minus 1 and Tn minus 2.
So you add them.
You add them. What's going to be the next term?
19.
19, exactly. So this is the same thing as the Fibonacci pattern, right? But for the Fibonacci pattern, you have to start with 1, 1. This is a Fibonacci sequence or Fibonacci pattern. But the idea is the same for this one. To get the next term, you add the 2 previous terms. So this will be the recursive relationship. Tn is Tn minus 1 plus Tn minus 2. Cool?
Mm-hmm.
Sometimes you just have to see it. And again, that's easier said than done. If you see it, it's like super easy, but it's not always easy to see it. Let's try this next one. And this one looks very simple. So we have n, our term number. We have Tn, our term itself. So for the first cube, we only have 1 cube. How many cubes do you have for the second?
8.
What about third? You can always count them out, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this front face, we have 9.
So 27.
27, yeah. So you see the pattern there? What's the pattern? What's Tn? How many are there gonna be in the fourth one?
64.
64, right? So what did you do to 4 to get 64?
Cube it.
Cube it. So Tn is gonna be n cubed. And that's the general pattern. Cool?
Mm-hmm.
And that's it, right? 5 is gonna be 125. 6 is gonna be 216, yada yada. How many cubes does Sarah need to build the 15th cube? So again, very simple. We're trying to find 215. That's going to be 15 cubed. It's a lot of cubes. And that's the answer to the last question there. Just 15 cubed, and that's how many cubes you need to build the 15th block. And you are done with this question. This wasn't so bad because the pattern was very simple. This next one's also a very simple pattern, I think. We've already done it. What's the fourth term here?
X to the power 4 plus 4y.
Easy peasy. This next one could be a little bit more difficult. This one is indeed difficult. Again, you need to see it. I'll give you a hint. It's dependent on n. It's not dependent on the previous term. It's just dependent on what n is. Here, why don't we think about it this way? I'm going to find the ratios, okay? I'm going to find the ratios. Check this out. 9 over 1 is a 9. 29 over 3. Sorry, 29 over 9 is going to be 3 point something. It's 3.22. This over this, 67 divided by 29 is 2.31. This divided by this is 1.92, yeah?
Mm-hmm.
And then the next one would be 221 divided by that would be, it's 1.71. So it's actually not approaching any number. It looks like it's gonna get smaller and smaller and smaller. So it's not approaching anything. What that tells us is that you're not multiplying anything to get the next number. What this means is that you're multiplying to and adding or subtracting some number. This is not how you get the next number. That's what this tells us. If these ratios were approaching a certain number, then we would have the multiple. But here that is not the case. I'll give you a hint. Here's the hint. 9, and again, you have to be able to see it. What I looked at when I saw this was I know 9 is 1 away from 8. 29 is 2 away from 27. 67 is 3 away from 64. You see the pattern?
Mm-hmm.
This is 2 cubed plus 1. So that's our second term. Our third term is what? 3 cubed plus what?
Plus 2.
Plus 2. So that's T3. So what's going to be Tn? It'll be n cubed, yeah?
Mm-hmm.
N cubed, you cube that number. And what do you add to n cubed? I'll give you another one. This is 4, 3 plus 3. This is 5, 3 plus 4. This is 6, 3 plus 5. So what are we adding that has to be in terms of n. So this was T4, this was T5, this was T6. So in terms of n, what are we adding?
Tn minus 1.
Not Tn minus 1, just n minus 1. The term number itself, okay?
Mm-hmm.
Doesn't rely on the previous term. Tn minus 1 means the previous term. That would be the recursive relationship, but here we have a general pattern. We have a cubic function, in other words, like this one. And it's a positive cubic function, so y-intercept of -1 would look something like this. So the next term is going to be, again here, it's going to be 7 cubed plus 6, 8 cubed plus 7, 9 cubed plus 8. Those three are going to be the next three terms. You see it, right?
Mm-hmm.
And that's how you do this question. Again, I know it can be tricky. So the first thing you want to check for is whether the ratios are approaching anything. Wasn't the case here. And the next thing was these numbers are fairly a couple units away from perfect cubes. And turns out you just add one number less than n to the perfect cubes to get it. Let's look at this one. It says determine the type of sequence. Remember, for arithmetic sequence, it's a linear line. It's a straight line. For a geometric sequence, it's going to be an exponential function. So let's look at A. Is that geometric or is that arithmetic?
Arithmetic.
Yeah. Because here the things are going to be 5, 10, 15, 20, right? That's the pattern.
Mm-hmm.
5 times 1, 5 times 2, 5 times 3, and you see that you're adding 5 each time. So that's going to be an arithmetic sequence. What about B? Arithmetic or geometric?
Geometric.
All right, let's check that. So T1 will be 3 over 4 plus 3, 7. T2 will be T over 16 plus 3, that's 19. T3 would be 3 over 4 cubed, 64 plus 3, 67. If they were geometric, R has to be exactly the same. Cannot be approaching something, can't be off by even a single decimal. R has to be exactly the same. What I'm going to do here is I'm going to do T2 over T1, and then we're going to check whether that is equals to T3 over T2. If these two are equal, it's going to be geometric, otherwise it's not going to be geometric. My prediction is this is not geometric because this is not an exponential function. You have an exponential function in the denominator, but you're doing 1 over it. So this is actually a reciprocal function. It is not a exponential. So let's check. T2 over T1. So it's going to be 3 divided by 19 divided by 3 divided by 7. So that is 7 over 19, which is 0.368. Now let's do the same thing. T3 over T2. So that's 3 divided by 67 divided by 3 divided by 19. That is 0.283. So is that a geometric sequence?
No.
No. R value has to be exactly the same. So in this case, it doesn't work, okay? So it's neither. B is neither. Let's look at C. C actually you can tell from right now, you can just straight up say what it is. Is it geometric or arithmetic? Look at what we're doing. To find the next term, we're subtracting a constant from the previous term. Is that arithmetic or geometric?
Arithmetic.
Yep, and done. D is again very simple. To get the ratio between the next term and the previous term is -2. So the ratio appears to be the constant. So is that arithmetic or geometric?
Arithmetic.
No, because you're multiplying, it's a ratio, it's gonna be geometric. So for D, here, look at this, T2, or you can write it like this. I'm gonna multiply Tn minus 1 on both sides. Tn is -2 times Tn minus 1. So T2 would be -2 times T1, 4. T3 would be -2 times T2, -8. T4 would be -2 times the previous term, 16, right? We started with -2, and these are our numbers, -2, 4, 8, 16. We're multiplying -2 each time. So is that geometric or arithmetic?
Geometric.
Yeah, because the common ratio 2 is a constant, so therefore it is going to be a geometric sequence. The last one, we don't know. We can't just say. We need to write it out for the last one. I don't see how we can say it. So we have 8 and 11. And the next term, T3, is 2 times T2 minus T1. So it's 2 times 11 minus 8. That's 22 minus 8. That's a 14. T4, 2 times T3 minus T2. So 2 times 14 minus 11. 28 minus 11 is a 17. You see the pattern? Is it arithmetic, geometric, or neither? Can give you T5 as well if you like. So that's going to be 2 times 17 minus the previous term, 14. So that's 34 minus 14, that's 20. So what kind of a sequence do we have here? Geometric, arithmetic, or neither? It is. You're adding a 3 each time, yeah? So it's going to be arithmetic. That's it. You're done. Yeah, that's it's an arithmetic because you're adding a 3. So look at this. You can write a sequence. I mean, we could have written this. So the question gave us the recursive formula. Recursive always uses the previous numbers to get the next number. But if we wanted to, for this one, we could write a general term as well, because the general term of an arithmetic sequence is a plus n minus 1d. Here a is 8, n minus 1 is just n minus 1, and d is the common difference of 3. So there we go. Using this general pattern, we can find any term for this sequence. But that is an arithmetic because you're adding a 3 each time. This one is a very common question. It says the number of seats in the rows of a stadium form an arithmetic sequence. 2 employees of the stadium determine that the 13th row has 189 seats. So we know T13 is 189. And we know T25 is 225. And the question is, what's T55? So that's all the information we're given. Now, remembering that the general sequence, general term for an arithmetic sequence follows this formula. Tn is going to be a plus n minus 1d. So if you use this formula for T13, you're going to get an equation. What's the equation? We don't know a and d. So A we don't know, so A is A. And we do know N is 13, right?
And
So-
then Tn is 189.
So this will be 12D. And Tn is 189. And that's our first equation. A plus 12D is 189. What's our second equation using the same exact formula? A plus how many D's?
24.
24 is perfect, yeah. Like that. And now we have a system of linear equations, right? See how it always comes back. We subtract here, by the way. We always subtract here. So it's going to be 36 equals 12D. D is 3. Plug that back in anywhere to find A. A is going to be 189 minus 36. So that's going to be 153. A is 153. And the question asked us for 55. So T55 we know would be A plus 54D. You're always subtracting 1 from the N. So this will be 153 plus 54 times 3, the D value. Plug that in and you're done. Easy enough. So if they don't give you A and D, they won't. You're going to add or subtract. What about if it's like this? Let's say T4 is 20. And let's say T5 is, I don't know, some number. 36. Let's make this 12. Let's make this T8. All right, so this is our thing. Fourth term is 12. Eighth term is 36. The question says this is a geometric sequence. And the question is, what's T10? So again, we need to set up two equations. The general form of a geometric sequence is this. So tell me, what does T4 become if you use this formula? The only known is Dn. So again, like we did last time, we don't know what A is, we don't know what R is, but we know N is 4, so it becomes R cubed. For the next one, it becomes R to the power 7, yeah, like that. Remember here, you divide, okay? You need to divide because you need to cancel out the A's. You can't subtract them. You need to divide. So 12 over 36 is 1/3. A over A gone. R3 over R4 is R4. So R4 is 3, therefore R is the 4th root of 3. And you can plug this back in to find A value, and then you can use this exact formula again to find T10, and you're done. So again, we get a system of equations, but here these are not linear equations, these are exponential equations or polynomial equations. You need to add or divide to get rid of the unknown. All right, cool. Let's call it a day there for today.
Okay, thank you.
See ya.